Okay, hello everyone. First of all, thanks a lot for coming to our talk today. My name is Marcin Panek, and I'm here together with my colleague Tomasz Wierzchowski, and we are here to talk about robotics. As you can tell by the slide, we are from Bosch. And yeah, robotics, but it's not going to be a journey through one-page long math equations, so don't worry, it's not going to be that boring. And we also have some cool pictures of robots, so at least that's going to be hopefully interesting. When it comes to the agenda for today, we're going to start with a few words about where we come from, so basically what we do at Bosch. We're also going to say a few words about our personal backgrounds. And then we will explain what we mean by the robotic and autonomous systems, and we'll try to convince you that those are quite complex, and hopefully we will understand why. Then we're going to say a few words about software development for robotic and autonomous systems. Here we're going to say a few words about software architecture, overall quality assurance, and some struggles that developers have to deal with on a daily basis. Finally, we will share with you some details about our new project, robotics project, that we are actually right now starting at Bosch. So yeah, hopefully that's going to be an interesting real-life example for you. Tomasz, why don't you now say a few words about Bosch and what we do there?
Absolutely. Thanks, Marcin. So my name is Tomasz Wierzchowski. We'll introduce ourselves in a bit moment. But what we wanted to start is a very quick intro on what Bosch does, because not maybe all of you understand the all markets that Bosch is in, and this is quite important for this presentation as well, for the context. So Bosch is a multinational engineering and product services company operating in 4 major business sectors, which is mobility solutions. We are tier 1 automotive supplier, but also off-highway vehicles supplier. We operate in industrial technology sector as a solution and component provider for manufacturing technologies. We operate in energy and building technologies, as well as consumer goods, which is probably where you probably know the Bosch brand most from. Fun fact, Bosch is also a semiconductor manufacturer of MEMS sensors, for example, accelerometers at your mobile phones. Another data point about us, so me and Marcin are representing Bosch Global Software Technologies, and this is a software engineering company of Bosch, which serves all of these sectors as internal of our internal customers. And we have development centers located all over the world, including Poland, India, Mexico, and Vietnam. And we are representing a new engineering center in Poland, established around 2 years ago. And we have a short video introducing our Robotics Autonomous Systems group here, and then also a bit wider context of our center, which we wanted to start with.
Our center in Poland will provide BGSW the ability to further strengthen its engagement with Bosch GBs and external partners by leveraging the geographical advantages and talent ecosystem of Poland.
Hi, my name is Tomasz Wierzchowski, and I'm leading Robotics and Autonomous Systems practice here in Warsaw. I have rich industry experience bringing robotics and software-defined products to a wide variety of markets, including consumer appliances, industrial inspection, construction, and agriculture. Here, we work hand-in-hand with Corporate Research Advanced Autonomous Systems Group and Bosch product business units to bring state-of-the-art products to life. Our team has extensive expertise in product development, as well as competencies in robotics software, algorithms, and product industrialization. Through this, we provide our partners with scaling capabilities in joint pre- and series development projects. Yes, so this was a short introduction. We represent Robotics and Autonomous Systems Group within our engineering center, and we focus purely on software development for those systems. Now, a bit introduction personally about myself and Marcin. I'll start with myself. So you heard a bit about the introduction by myself on this video, just to make it a bit wider, and also to give you some examples of products that we worked on. We have some follow-up slides. So again, my name is Tomasz Wierzchowski. I'm coming to Bosch and to Poland with over 12 years of engineering experience building and robotics teams, as well as building products within the robotics and autonomy field. Also, I am very much passionate and I would say evangelist even on robotics, deep tech, and startups. Most of my career worked for robotics startups, actually, outside of Poland, which I will talk about this later in next slide. And I actively publish on these topics on specific conferences and in my blog. Some example of projects that I worked on, which are relevant. Also, this is a quick intro to robotics and autonomous systems. So I had the privilege to work on one of the first commercial drones project in Netherlands back 2012, before DJI had actually a first product in the market. Very interesting experience when I was leading the systems engineering team there. I work at Dyson, which name you might know, in their headquarters on their first fully autonomous robotic vacuum cleaner based on visual SLAM technology, which I will show some video in a moment. I work for a startup called Emotech in London, developing a personal robot with evolving personality, which was awarded at CES with 4 awards in 2017. I also was leading an engineering at British startup ABC, developing hopping robot for scouting of crops. And here are 2 videos just showing some insights of these projects. On left, you see what the visual SLAM is, which is pretty much a localization technology, which is indoor GPS, which triangulates, in simplified words, a position of the robot with under centimeter accuracy within the home without using any external markers. And on the right side, you see the hopping robot and the principles of operations and how it scans and up to 100 hectares per day. So this is the more or less type of projects I had experience with. And with that experience, I'm coming today with Marcin to present some insights of those projects and some general software development practices. So Marcin, why won't you introduce yourself right now?
Sure, thank you, Tomasz. So for the record, my name is Marcin Panek, and I have roughly 7 years of experience in embedded and robotics software development. Since robotics, I mostly use ROS, which is Robotic Operating System, quite popular framework or even whole ecosystem used in robotics and autonomous systems industry. Together with that comes Gazebo, which is like the simulator for robotics, and we're going to say a few more words about this later on. When it comes to programming languages, it was mostly C and C++, as those still tend to be most used languages in robotics, and also a little bit of Python for some overall tooling. And now at Bosch, I'm also diving a little bit deeper into systems engineering practices just to support overall project lifecycle for the robotics products. But about this, we will also say a few more words later on. Now, when it comes to example of my past projects, 2 most interesting ones are Elo's robot, which is like the sort of humanoid service robot to support elderly and elderly care places, or just deliver some goods at hospitals and similar use cases. There I worked at the robotic arm motion control. So basically a lot of embedded stuff for robotics together with some robotic algorithms for robotic arms. And the other project was at Unit and Mower. That was basically the outdoor robot. In this case, that was just a mower, like the industrial grade mower. The one you typically sit on. We tried to come up with the system that solves that trouble for you. And there I focused on the overall outdoor robotic navigation and localization, and also on overall system design and integration. Yeah, and that was not only the marketing part. We just wanted to give you an example of what kind of interesting projects big companies are doing in Poland, actually. So as Tomasz mentioned before, we have now a research center in Warsaw, and just this was like the background of the projects that we are, we used to work with, and now we bring this expertise to other similar projects, right? So now let's move on to the robotics and autonomous systems part. So we want to explain what we mean by this term. So Tomasz, maybe if you could just quickly go through the examples we prepared for today.
Absolutely. So first very important thing is to define what we mean by robotics and autonomous systems, because you might have coming with different backgrounds. Your understanding of robotics might be different than ours. So what we are talking about today and what we are typically working in past and today, we are at Bosch. You've seen some glimpse of that already in our introduction, but just to be very precise, what we are talking about are the typically mobile robots, so robots that move from point A to B, perform some kind of mission, and have some degree of autonomy. So this is a very brief introduction and definition of robotics autonomous system. Some examples of projects you see here on the photos, starting from Astro Robots from Amazon, which is a home robot trying to enter a different use case than cleaning robots so far. Then you see the agriculture robot for weeding of vegetable farms from Nio Technologies. Then you see a cleaning robot, actually first generation cleaning robot from Bosch called Rockster, which is probably this category of robotics products are the most widespread robotics products in terms of numbers sold, definitely in consumer market. And then the last example is food delivery robots. So you see the kind of different applications just in here, showing that we're dealing with very wide ranges of business cases and applications. And that's where the complexity, I would say, starts. And I'll hand over now to Marcin, so he starts explaining a bigger picture on the software engineering and systems part.
Yeah, so let's have a look at the under the hood of robots. So if I were just to simply describe what robots do, it would be just sense, think, act. And you might have heard this term already because it's getting quite popular now when it comes to autonomous systems and especially to autonomous cars, probably. So basically, we have this closed loop between the environment and the robotic system. The environment is basically any place the robot is supposed to work with. So it can be, like, hospital. It can be backyard of your home. It can be, for example, your household, and you want your robot to clean there. So basically any arbitrary environment for the robot to work with. And then we have the sensor part on the robotic system, which is like the input for the whole system to sense the features of the environment and to understand this. Then we have the sense part, which is like first step of intelligence, let's say, which tries to understand features and tries to map them into some internal representation in order to then be able to plan within this environment. And an act. Acting is done by the act part, which is like the part of the intelligence which tries to think how the robot should behave and design the motions, for example, for the robotic arms or the mobile robots. And then we have the actuators, which is just basically a set of mostly motors driving the robot around. Now, if I were just to mention like what is the crucial part or the most challenging one, I would say that it's just achieving the robust operation in previously unknown environment. And what I mean by that is let's take another let's take again example of the vacuum cleaning robot. Say you develop a robot like this in your lab and you test this a little bit in your lab, then you test it a little bit in the household of your developers, and then you ship it to the market. The robot needs to work there robustly and always. Like it cannot be confused or get stuck because it's so an object that it has never seen before, right? So this again still might sound like it's just a little bit of testing, and it should be still easy, right? But we wanna give you two examples of just some small sub-problems of the whole system. And the first example is let's take an example of the service robot I mentioned in my bio part. So let's say we have a robot with wheels driving around the facility, and the robot has 1 or 2 arms and wants to, I don't know, let's say it's a hospital and the robot needs to deliver meds to the patients, right? And the hospital is multi-level building, and it needs to, and the robot needs to operate in this environment. And say we are not allowed to anyhow integrate any part of our system with the elevator control stuff, right? So in the end, the robot needs to be able to operate the elevator panel. And like to do this, robot first needs to safely enter the elevator. Remember, it's a crowded place probably, and it's also quite tight space. Then it needs to recognize the panel, and you can just see at the pictures how many different kinds of elevator panels are there in the market all over the world. So the robot needs to understand like where are the buttons, what the buttons mean, where is the floor I need to go to, how do I approach the elevator planner. So it needs to plan the motion, again, tight space and crowded places elevators are. So now we are just approaching the button. Then it needs to think how the button should be pressed, like what should be the angle of the end effector approach. Then we need to sense the feedback from the elevator planner, right? Sensing this with the force sensors is quite hard, so we may try to do this just by looking at if the light comes on. But again, this needs to be robustly recognized for all different kinds of panels, right? And then the robot needs to, of course, go into some resting position and recognize when is the correct time to leave the elevator. So basically when the correct floor is reached, right? And then again, crowded place, leave safely. So that's just like the one sub-part of the whole system. We are not even mentioning here operating between the patients, for example, recognizing the tables where to put the meds, where to take the meds from. And yeah, just like all of those sub-problems I mentioned, and this sub-problem is probably a nice research field for a couple of years of study, right? Tomasz, if you could just say a few words about the other example we prepared now.
Absolutely, thanks, Marcin. So another example now is from my experience, is a cleaning robot operating in, here example, just subset, dining room in smart manner. So this maybe sounds simple, like what's the problem? We want to clean our dining room. But if we think from the perspective of the robot and environment, It's actually not as simple as you might think, even though maybe there are already products on the market that kind of solve it for last decade or 2 decades. So let's try to deep dive into this for a moment. So what challenges we see here on these photos, for example? So one challenge on the photo on the very right side is you have something what we call in robotics, in home robotics, a forest of chairs. So what it is, maybe it sounds funny, but it's actually not very funny for developers because you need to navigate in very cluttered environment. For the robot operating on the floor, it has to navigate through tight spaces between these very tiny, for the robot, for the sensors you typically have, so either 2D LiDAR or a camera system, not really expensive camera system. You need to navigate there. You want to, on one case, not get stuck, look smart, do fast cleaning, and clean all of the spaces where the robot can get into. So you need to have quite sophisticated perception system with low-cost sensors, as well as quite sophisticated planning algorithms and stack to navigate around them. Another example is not getting stuck on objects. And those objects doesn't have to be very untypical objects. Maybe all of you have objects that one particular robot vacuum cleaner will get stuck, which can be one IKEA chair, example, or one bar of the coffee table. And the challenge is that robot maybe is not designed to really able to climb all of these tables, which there will be hundreds or thousands types of around the world. And once it gets stuck, also it needs to recognize it and gets unstuck. So this seems, again, simple, but you need to tackle an open world scenarios in these type of systems. So this is 2 environmental examples I want to give, which shows complexity. Now different dimension, so hardware constraints. So every system, every mobile robot, or most of them will rely on its onboard hardware. What we call onboard hardware is a computation, sensors and actuators. So starting with computational units, you always will have a computational resources limitation, either it's CPU power, RAM, flash, or some accelerator power, which means you need to really think ahead how you will be designing your system. And Marcin will be talking a bit about this in some later slides. But one thing to consider, on top of these complex environments use cases, you have limited computational power. Also, some of the, to make it even harder, some of the processes and tasks will run in parallel. So perception system replanning, they might need to run in parallel, and they are not necessarily the most lightweight algorithms that you need to deliver to solve these complex use cases. And finally, you will need to fight a compromise between sensors and actuators, quality versus price. So maybe if you are not in robotics consumer market, where the price is super low for the bill of material that you have to deliver to make a product relatively cheap, or to make business case viable, maybe this is not as difficult in maybe off-highway vehicles like excavators, but always there will be limitation regarding the price of the sensor and the quality of data you get from it in simplified words. And now the final, let's say, additional complexity challenge is the type of robotics platform. So far we're talking about typically wheeled robots, right? That we're describing a cleaning robot, maybe, okay, one with manipulators. So we can add multiple different dimensions of degrees of freedom of robots. So we can add manipulators to moving platform. We could change wheels to legs. We could add propellers, so we can make a flying robots. And that's completely another level of complexity because you need to solve control challenges as well as other challenges related to robotics platform related to this. So that's concluding the first part regarding robotics development for and complexity of robotics autonomous systems. I will hand over to Marcin for the software part.
Sure. So now let's move on to the software development for robotic and autonomous systems. And I would like to start this part with saying a few words about the development lifecycle. So basically, it all starts with understanding the objectives and the environments. So basically, we need to understand what task needs to be done by the robot and also where it needs to be done, right? Based on this, we choose the robot type. So basically, we choose the proper tool for the job. And only then we start looking into robot architecture. And by this, we mean proper selection of sensors and actuators, together with control algorithms for actuators and some perception algorithms for the sensor part. and also the logic, let's say, of the robot, so the planning concept, and then some execution layers, right? And I want to emphasize one part here. It might seem quite obvious that you need to understand what you are doing, but quite often it happens that people try to solve some very generic problems. Like, let's say you might have seen startups trying to do agriculture robot, right? But what is really agriculture robot? There are so many things to be done in agriculture that it's really hard to make a generic robot that solves all of those issues, right? So you have to specify one particular problem, try to focus on this, and then design the robot around the problem, because we are unfortunately not yet there to make some generic, very multiple-purpose robots, right? And we brought some interesting quote here by Dr. Mike Aldred, who is robotist, and he is a senior principal engineer at Dyson. And in one of his talks a couple of years ago, he said that robotics is just an enabling technology. It's not a product in itself. So basically, it means that you shouldn't start a project or a startup that is doing robots. You should just start a project or startup that is solving one problem with a robot, right? So it's about the problem, not the robot itself. And what can be helpful here in understanding this and diving a little bit deeper into details of your environmental issues is the system engineering practice, right? And if, Tomasz, you could just say a few words and demystify this beautiful term for us.
Absolutely. So for some of you maybe coming from automotive or aerospace backgrounds, this is not a mysterious word, systems engineering. But in general, what we're talking about. So Marcin was talking about approach for developing robotic systems. So robotic systems are complex systems, and they are not the only complex systems, both software, hardware, that are domain that other companies are working on. Aerospace, automotive, defense, they are also, some of you probably are from these domains, developing complex systems. And there is methodology and domain called systems engineering, which already has tools and methodologies, again, some methodologies which tackle this complexity. And without going into too much details, systems engineering is a set of tools, methodologies, processes that you use to deliver complex systems, making sure that you tackle the requirements, the market requirements, the customer requirements, the regulatory and complexity of environment and all of the domains in a way that you're not only focusing on one domain like robotics, planning, or maybe cost optimization, but you bring them all together. And one great example of this is what would happen if systems engineering would not existing. For example, in aerospace industry is shown here on the right side. So what you see here is a set of perspectives of different domain engineering teams designing an airplane. So for example, if power plant group was the only group who was driving the requirements and sizing of aircraft, we'll have an aircraft which you see on the bottom right, which bottom, which will have super large propeller and super big fuselage, but it won't be able to fly in the end. But it will have great lift, for example, force. And more and more. So this is we could draw a similar example in robotics if we are designing a great robot which has great localization system but cannot do the job, cannot do the frequent scanning of crops, or it's too expensive, for example. So this is just a quick example of why systems engineering is something that I highly encourage you to look into in complex systems and robotics. And back to you, Marcin.
Thank you. Now the good part. What we are looking at now is the full stack for robotic system. It's not one particular system, it's like the generic view. And by the way, this comes from an awesome book called Robotics for Programmers by Andreas Billmeier. And I think it's a very nice book, first of this kind, really explaining the complexity of the robotic systems, but in quite a comprehensive way. So if this is something interesting for you, I definitely recommend reading. So now if we could just have a quick look at layer by layer to understand what we have here, we start with the bottom one, which is the hardware. And hardware in robotics is basically sensors, actuators, and overall compute power, right? So the middle part is actually quite common for all embedded systems. What makes it a little bit different for robotics is the sensors and actuators part. By sensors, we mean everything that is used to sense the environment by the robot. So it can be cameras, lidars, radars, or ultrasonic sensors, anything like that, but also everything that is used to sense the internal state. So for example, wheel encoders to monitor the speed of the wheels, but also some temperature sensor, for example, for the health management and monitoring, right? Then for the actuators, we have mostly wheels and together with the gearing and motors for mobile robots to move around. But also every kind of motor and gearing for the robotic arms. So basically, if you want to have robotic manipulation, in our project, one of the actuators will be, of course, the manipulator arm. Now, when it comes to the compute power, we quite often combine a couple of kinds of compute power. So we typically use PC computers for the intelligence, let's say overall, and some low-level microcontrollers to control the motors, for example, right? So we are definitely talking about the distributed systems in robotics, and it's both distributed hardware and software, right? Okay, the next level is operating system. And in robotics, it's quite often real-time operating system, especially whenever we talk about motion control. And apart from this, it's quite the same when it comes to other embedded systems. So we for sure have here things like memory management, scheduler for the kernel, some networking stuff. Yeah, pretty common stuff for embedded systems. Now we have some generic system services, which is like basically the underlying layer for the robotics part. So we have some common leaps that are not only used in robotics, but robotics makes use of them. So for example, we have here, for sure, package managing, if we want to have deploys of the software for our robot. We have some logging facilities for sure. We have also some math leaps for the algorithmic parts. We have machine learning stuff, also computer vision for the perception parts, right? And tons of other that we do not have time to dive deeper today. Sorry. Now the robotic part, so-called robotic-based libraries, and this is basically a set of libraries implementing various algorithms for robots. Those algorithms are for trajectory execution. So basically making sure the robot follows the path that was planned during the path planning phase. And we have a bunch of libraries for this and a bunch of algorithms studied for years in academia now. We have also things like mission control here, behavior trees, quite interesting piece of architecture here, quite common and popular now in robotics and comes really from the gaming industry, I guess. And also all parts of the navigation localization to localize the robot in the environment, right? And now the highest layer of the architecture here is so-called robot application. This is a very abstract version, quite specific to the robot you are working on. And this could be named, for example, like the execution layer. So basically everything that is needed to orchestrate how the robot behaves and when it does the job. So basically, for example, you have a vacuum cleaning robot. So on this layer, you would monitor if you have enough juice in battery to finish the job, right? And you would probably order lower layers of the software to go to the charging station to recharge battery and then continue the job. So now this connects quite nicely to the sense, think, act approach I mentioned before, and we can see mapping here of all the layers I mentioned on the slide before to the sensor, sense, plan, act, and actuator part. So basically, on the hardware layer we have sensors and actuators, and of course the whole compute power. Then we have real-time operating system, again sensors and drivers, sensor drivers and actuator drivers. And all other things that are required in any embedded product to work. Then we have the generic system services, which are like again underlying layer for the robotics algorithms. So we have some computer vision labs, logic leaps for planning. So let's say the robot intelligence, and then we have some optimization leaps, which are heavily used by various algorithms in robotics. Right? For example, the trajectory execution part is using this a little bit. Then we have the robot-based libraries, which is like the proper algorithms for robotics. So again, localization, path planning and navigation, and then we have trajectory execution and control of the robot. And then very abstract, again, layer that is quite specific to the exact project you are working on, right? Okay, so now let's have a look at the quality assurance in robotics. And since we mentioned the systems are complex, testing them is also quite complex. So a few things to mention here are definitely the number of test cases to cover various cases where your robot may end up. Then next thing I mentioned that those are quite complex and distributed systems. So we have many software and hardware modules involved that needs to be integrated properly. And yeah, before you test, basically you need to make sure that all the versions are matching and everything is there, right? Now, if you develop a robot that needs to do the job in the field, you sometimes need to test the full mission run, so-called, right? So let's say we have the mowing robot, and due to specification of your product, you support some big backyards, whatever big means here, right? So from time to time, it's good to put your robot during the development phase, of course. It's good to put your robot in the field and make sure it succeeds in the biggest supported area, right? And this can be time consuming, right? Mowing a backyard can take, I don't know, an hour and a half, and you have to wait for the results. So it's not something that you can do every minute. It is time consuming. And finally, some tests are really hard to do outside of the season. So let's take, again, an example of agricultural robots. It's hard to test harvesting, for example, in winter. So if you are a developer for robotic system and you are doing agricultural robots, you need to make sure you collected enough data during the winter, during the summer, so you have something to work on during the winter, right? Because it's hard to take the robot in the open field. Another example here would be the delivery robots. You might have seen this video in the internet previously. This is the delivery robot getting stuck in the snow. So again, an example of a system quite hard to test outside of the proper season, right? Okay, now the next part when it comes to quality assurance is the simulation. Simulation is quite a vital part of robotics development. And by simulation, we mean basically the virtual recreation of the environment where the robot is supposed to work, right? And you can technically think of this as of the computer game. I think some similar techniques are used to implement those both words. But it's not just gimmick we use in robotics to entertain ourselves. It's actually quite important part of the testing strategy and overall pipelines, because to test a robotic system on the top level, you need to generate a lot of test data for the system. It's not like a unit function. You put 2 arguments and you make sure the output is as you expected, right? So we actually need the simulation to generate those set of data and also to have the expected outcome, so some sort of ground truth, let's say. So it's again not a gimmick. It's unfortunately something that we have to use. Nice thing about this is that we can use this in a headless mode. So we can basically run this without graphics, and we can run this on the CI/CD pipeline. I will say a few words about this in a minute or so also. And yeah, but this unfortunately comes at a price, so you have to put some effort in creating the virtual environments and also maintaining this. This is still a piece of software that comes with some configuration, some utils and things like that. So again, a little bit of maintenance there. It does not reflect the real world like one-to-one. So basically, you tested your robot in the simulation, works perfectly fine. It doesn't mean you can ship it to the customer and will do the job there. Yeah, unfortunately, still some real-world tests are required. Also, including the real hardware that you are using in the product is quite tricky in simulation. Some parts of this can be done, but it's again comes at the price. And then for those of you who ever worked with ROS or Gazebo, you might have seen that those tests are quite often pretty flaky, and it's again some cost of maintenance of those tests, because you sometimes have to solve problems that are only unique to the simulation and will never occur in the real world, right? Now we have example of a robotic simulation running. So again, for those of you who are familiar with ROS, on the left-hand side we see RVs. So this is basically a tool for the, let's say, monitoring and visualizing the data of the robot. We can see here both the data from the sensors and also some debug data from the algorithms. On the right-hand side we see Gazebo, which is the simulator, together with the virtual household, and we see their residential robot doing its run, right? So again, on the left-hand side, we see some paths that the robot is expected to follow, and this is just basically the debug outcome of the algorithm. So developers can have a look at what is going on, because otherwise it's really hard to see, like, looking at the series of ints and floats to understand, like, what is the output of the algorithm. This is actually the only way to make sense out of this. And again, this can be run headless, and you don't have to look at this, but still get some valuable data from this, right? Now, moving on, we go to some struggles, so daily developer's life. And before I start diving deeper here, I want to make one remark. So what I'm going to say in a few minutes will probably sound a little bit like I'm stating the obvious, but we have to remember that robotics is quite often the world of proofs of concept, startups, small teams, and demo-driven development. So we quite often don't have much time to invest in proper tooling and stability of the system. And unfortunately, this backfires at us as developers. So it's quite often just hard to use the robot during the development, basically, and there's a number of reasons for this. For example, again, distributed systems, so we can have mismatching interfaces between modules. Quite obvious thing, but again, in a small team, it's another effort that you need to deal with. You are working on a prototype in an early stage, so you might have some hardware issues. So you basically try to run your robot and do some test of your, let's say, high-level logic algorithm, and there are some like hardware issues, and the hardware is behaving funny, and you don't really want to spend time fixing this. You just wanted to test your high-level algorithms, but again, you have to deal with this, and sometimes I don't know, solder some wires and make things right again, right? Then we have some software bring-up issues. So this again connects a little bit to the distributed system and hardware issues. So basically, everything is waking up. All the modules are brought up. There might be some issues with mismatching modules, interfaces, and things like that. And sometimes it's tricky to debug those. Quite often we end up with some undocumented manual steps required to run stuff on the robot. Again, this might be something that is quite common to other domains, not only robotics, but we see it quite often in small teams. And again, we have quite often small teams in robotics projects when they are in early stages, so definitely something that happens here as well. And also, you might be working in a remote location, and you only have a few prototypes of your robot in headquarters, so you don't have hands-on access to your robot, and sometimes you end up making just some small, tiny adjustment that will never break anything on the robot, but then it turns out they broke the robot, and the robot doesn't work anymore, right? So yeah, untested changes in the upstream repository. Yeah, so how to deal with this? I would basically say that you have to encourage the proper mindset in the team. The team needs to understand that it's quite important to keep the system stable throughout the whole development lifecycle, because it speeds up the testing and you know, trying researching some algorithms, for example, and things like that. So some tools that are quite useful here are definitely tools for example, code deployment. So you develop something locally, you want to test it on the robot. It should be as easy as possible to just bring your code to the robot, make it run, and see some outputs. Then the robotics application launch. And what I mean by that is that in early stages of the development, you quite often don't have like ready user interface. In the end, you will probably have some fancy, nice-looking app to control your robot, but in the first days, there is nothing. There are some bizarre scripts written by someone, a lot of code, hard to understand how to break the robot. So it should be quite obvious for the team to develop something that makes the robot easy to use and for example, command it to go somewhere, do the job. Then we have error handling thingy. What I mean by that is that quite often we have some weird errors that appear during development, and it's nice to be gentle to developers and inform them about what is happening on. So let's take example of a robot which has like one high-level PC and microcontroller. The microcontroller needs to have firmware of some certain version to be able to communicate with the PC, right? So it's nice to, for example, check this versioning and inform the user if there's something is going on there, then just instead of just blindly trying to use the wrong version. And then you can also suggest some fixes, like modern pieces of software do. You get a prompt that, hey, for example, hey, the software on your firmware, the firmware version is not correct. You should consider updating this to make the robot work again. And then you can, for example, paste the command to do this. And then we have a bunch of introspection tools for like debug and development. This is just basically a set of tools that will let you understand what is going on in the system. Like the RVs I showed before is one of them, and ROS comes with a lot of those, but again, this needs a little bit of touch and understanding how to use them. Now I want to say a few words about CI/CD pipelines, and I'm not going to embarrass myself and go into details of those because you probably know this very well already. But just for the record, let's go through that and see what is different here for robotics. So we start basically with the happy developer, happily developing locally. He made some changes in the code, runs the bunch of tests and checks. The same ones are then run on the CI, and once the CI is happy with the changes, we go on with the merge. Once we merge the code, CI builds the deployment with the proper packages of the code. Again, nothing too new here, but what is new here is that we want to care about how to bring this to the robot. So basically, we want to combine this with a set of scripts that will make it easy to use it on the robot. So let's take the example of for example, test team that takes any arbitrary piece of code and wants to run this on the robot, just to make sure that the integration is there, everything is right, so they should be able to do this quite easily and quickly, right? And now moving on, we can put a little bit of more automation here as well, and we can, we can use the approach of robot in the loop. I think our video is not working. Sorry for that. But overall, what I mean here is that you can basically have like the whole piece of tooling prepared to automatically put the code on the robot in the lab somewhere, and the robot can run it itself, right? So you can, for example, test the docking or undocking of your robot. So again, a remote developer without an access to the... Oh, it's working. Thanks so much. Okay, so we have Jenkins here. Jenkins produces some artifacts, so deployable code, and then robot becomes the Jenkins agent. Robot downloads the code from the Artifactory and runs this. And there is some execution layer that deals with this automatically and monitors the motion of the robot, then collects the data and uploads back to the cloud. And I know it looks a little bit like the adult video, sorry for that, but we are not able to show all the details of our prototypes. But you can clearly see here is a docking and undocking robot. So yeah, basically you don't have to run this manually. You can even make this a part of your regression test, for example, and run this nightly or weekly. For this purpose, it's quite nice to have a Robotics Lab. We are actually building one in our office in Warsaw right now. So we basically want to recreate a home environment to test some of our home robots. And yeah, this comes together with the motion tracking system. You can know the motion tracking systems from the gaming or movie industry. And this is basically used to exactly and very precisely monitor the motions of the robot and make sure that it's doing the right job, and also the quality of the motion, for example, is correct, right? Okay, I think that concludes the part of the software development. Now, Tomasz, if you could just say a few words about the example of our project that we brought here.
Yes, thanks, Marcin. So, last example of this a bit maybe heavy presentation today is a bit of teaser. So we're not able to talk about details of projects we work on, but we are able to give you some overview of a bit different project than we've shown so far, related to Robotics Autonomous Systems. So this will be related to off-highway vehicles autonomy ecosystem. So a bit short intro, because not maybe all of you know what off-highway vehicles are, and why Bosch is in this space, or what's in general in the space. So off-highway vehicles are vehicles that typically don't drive off highway. Yeah, that's very obvious. But what you can think about is everything that is not a car, pretty much, in simple definition. So think about construction, mining, and agriculture, heavy machinery, mobile machinery that can move. And this is a very interesting market compared to automotive. You see, in automotive, you typically have one type of car. Okay, maybe there are small variations between them. In off-highway vehicles, you have hundreds of types of vehicles. And why I'm mentioning is why it's interesting, because the supplier market, and Bosch, specifically Bosch Rexroth, is a supplier for this market, requires a bit different approach than for automotive suppliers. So although you might be reusing similar technologies and similar architectures for ECUs, for example, and for software, maybe a bit similar, you need to serve hundreds of customers, and volumes are much lower. So what you don't have here is not built to spec. So you're not building ECUs and software to spec of each customer, because you're not going to manufacture millions of units per each manufacturer of your subsystems. But you need to design a more generic solution, a bit more like ecosystem. And this is a very major market already for parts, so for electronic control units which help to control hydraulic drives, for example, and maybe a bit of sensing, but it doesn't exist yet for the autonomy. And that's where actually Rexroth decided to invest, and that's why we'll be talking about this as a great example. So here is a short video which will show you what type of machines we're talking about and what applications. So think about, agricultural equipment, you will see in a moment, and construction machines like excavators. And this is quite actually big machines, and safety is a big part of it. And the other side is the steel manufacturer, which develops a final applications, final software, which is the application software in our stacks that we discussed before, Marcin was explaining. What you see here is actually already what's on the market. So Bosch is providing an ecosystem which provides OEMs to integrate some assistance functions, and of course the basic joystick control and HMIs for these type of vehicles. But what is the future is to enable the OEM manufacturers, smaller and larger, to build autonomous functions based on advanced perception systems as well. And that's what we want to tease you in a moment. Also, we have some very specific call for action after that. So again, one example to focus on, excavator or excavation. So a bit of history. First, we excavated by hands, then we invented simple tools, and then hydraulic excavator. Where we are now is that we have a hydraulic excavators which are electronically controlled. So it's pretty much control by wire, drive by wire equivalent. So we have electronic control units and drive systems which are controlled hydraulic by ECUs. And where is the future is the conditionally automated excavator, and finally beyond automated excavator, where there is not even a cabin for operator. And why this is interesting? Because still this market will not change in terms of the off-highway vehicles. It's many vehicle manufacturers, OEMs, producing low volumes relatively, or compared to automotive. So there needs to be a solution which fits all, if not most, and this needs to be ecosystem. And this needs to fulfill autonomy requirements. So what you need for that? So you need a hardware stack and software stack. And hardware stack for that, this is mostly sensors, because on the actuators, already each vehicle will have a drive system that they have their mission, either as excavation or harvesting in combines. But what they lack is the perception. So what you would see in these systems, and that's what some suppliers like Bosch will also deliver, is radars, lidars, ultrasonic sensors, camera systems. And on the other side, you also need a control unit ECU, which integrates not only perception systems, planning, but also functional safety. And that's something that doesn't exist yet. That's something that Bosch Rexroth is working on. And I'll leave Martin to explain a bit more on the software stack, and then we'll be summarizing.
Yeah, so just shortly, because we are running out of time, this basically is a little bit of simplified view of the software stack with a focus on, let's say, development groups. So we start with the base software at the very bottom, which is the operating system and all the middleware for the communication between the modules. And then we have drivers for all the sensors and actuators that we mentioned before. And you can see also the picture here on the hardware stack side. Then we have perception, which is the set of algorithms for terrain mapping, machine position, and detecting objects from sensor fusion algorithms, right? And then we have the top layer, which is application. And in this very case, we actually leave this application layer to the final customer. So basically, this is just an ecosystem that you can buy off and build your autonomy upon of this, right? And this comes with the functional safety, which is quite important part, and it's quite new thing for robotics. We don't have many robotics projects in the open world with functional safety certification, right? So I think this is really interesting. This is really challenging, and this is really something new on the edge. Hopefully, soon we will be able to use this in the open field, right, and build more autonomy. And that concludes actually our presentation with call for action. So if the project we showed you just before is something of interest for you, if this is a challenge you would like to work with, then just please contact us, as we are actively hiring for this project. We are looking for senior colleagues, so mostly for software architects with some experience. We think from automotive, because we see a lot of examples, a lot of similarities between this project and classical automotive, or the new automotive algorithms that are deployed right now in the field, right? So we are looking for the software architect, and we're also looking for senior embedded software engineers to join us on this journey, right? So again, if this is something interesting for you, just feel free to contact us. You can scan the QR code to see full JDs, and yeah. I think that's it.
Thank you so much.
Thank you very much.